All right, hi folks, and welcome to another update on Iceland. I'm geology professor Shawn Willsey. Today is Friday, December 8th, about 12:30 p.m. here Mountain Standard Time. That would put it about 7:30 in the evening over there in Iceland. What we'll do today is provide just a brief update on some things that have happened over the past 24 hours, and mainly what we'll spend our time doing today is on some question and answer from different viewers. So appreciate you sending questions in. Sometimes I try to respond to them in the comments. Other times, if I think they're good and appropriate, I just pull those over, copy and paste them, and then we just go through those. So we've got maybe 10 questions to go through. But let's go ahead and start with the update for today and what's been going on. No eruption as of yet, but a couple things that are new. Let's start with our data. We want to always separate data from interpretations or opinions. I think it's important to always divide the line between those two. I think it's a good way to tackle things in life. So if we look at the seismic data, and notice I have a nice huge cursor here that's sometimes in pink. So some of you will be super excited about that. I apologize if the cursor was small last time. Sometimes it's hard to remember to make it big for these videos. But there's our earthquake data for the last 24 hours. Again, that strong, prominent northeast, southwest trend. Most of the quakes are fairly small, although we did have in the last 24 hours one. There was about a 2.1 magnitude quake, about 5.8 kilometers depth. Right in that zone of that area of most concern, north of Hagafeld and just south of Sýlingarfell. So there's our earthquake data. Total number of quakes, maybe a slight uptick from yesterday, but generally about the same frequency that we've been seeing over the last few weeks or so. If we look at the GPS data and go to the station that is closest to the power plant where the uplift is strongest, make this a little bit bigger for you folks and then drag it over. So mainly we're looking at this graph right here. And so here is the uplift data, and so you can see since November 10th or so that steady uplift in the ground. Few anomalies in there, and there's a little change in the slope here, so it's much steeper right after the 10th, and then since then a little less steep slope, but still an upward trajectory there. So we're still seeing uplift right near the power plant, and we'll have to see how this goes moving forward. It would probably take it at least another week or so to get back to the same amount of uplift that caused the magma to move off to the east around the 9th or 10th of November. So that doesn't mean that anything magical will happen. If we get back to this 100 millimeter mark on this graph, it could well keep trending upward and the uplift could far exceed that. Remember that everything's changed in the subsurface. Whatever normal was prior to November 10th, there's a new normal, and we just don't know what that architecture looks like underground and exactly how that would play out should the magma continue to intrude and inflate into the area. So there's our GPS data, and looking at the Met Office update for today. This came through just a few hours ago. So the land's continuing to rise. It's Svartsengi near the power plant. Chance of another what they call magma flow. That's basically intrusion. It could end in an eruption. And let's see. So it's the event's not over. Land continues to rise at the same rate as the last few days, and there could be an eruption. It's most likely the magma will go back towards the dike that formed on November 10th. That's what they think is the most probable scenario. The most likely source of an eruption is north of Grindavik towards Hagafeld and the area of Sundanugiska, so the old crater line that's just east of there. Nothing can be said about when the next magma run will happen, and it could start at short notice. So this thing could accelerate quite quickly. Within a few hours, we could go from things looking like they are now to basically having an eruption. I've seen these things progress really quickly in Hawaii, and so we just don't know. It could continue to, slowly evolve over weeks and months, or it could ramp up quite quickly. Seismic activity pretty steady. And then the new hazard map. So I want to show you, they did put out a new hazard map. Let me get that in view for you. And so here's Grindavik down here. Power plant and the Blue Lagoon are right there in the middle. And I did Google Translate some of these terms over here. So they've got everything in 4 different zones. Zone 1, 2, and 4 are lower risk, and then zone 3 is the higher risk. Notice that the continuation we had earlier down here out to the ocean, that's no longer present. So there's enough evidence to suggest that a submarine eruption is less likely, and the extent, the linear extent of this intrusion isn't maybe as long as was previously thought when we had other data at that time. And so the different hazards here, if I got my translator correct, I'm sure our good Icelandic folks will correct me, but this first term here, which I won't try to pronounce, is basically fractures, so cracks in the ground that could happen. The one that starts with a J is earthquakes. So earthquakes are possible, especially in these zones here. I mean, and if there's a strong enough earthquake, if there's a magnitude 3 or 4, you would feel it in all areas, but that would be the area directly above that earthquake. And then this last term in zone 4 means, it translates to crack movements, which I'm sort of thinking means like subsidence. So this is only a hazard in zone 4 where they're actually seeing near the town sinkholes or subsidence type features that are occurring. And there's a little inset map here of the town area with these big black and hashed lines, and that word there, sprunger, translates more or less to I believe cracks or fractures. So that they've actually mapped those out as those run through town. Of course, these are maybe just the larger ones that have been mapped, and there's probably some smaller ones in there as well, as we learned. So, and then the orange zone, even though it has the same hazards as zone 2, I'm assuming that the chance is just higher, so the risk is just greater within that zone. So hazard maps are always a dynamic entity, and so we would expect, as the data and the risk assessment changes in the region, that the hazard maps should evolve and change as well. So I'm sure that'll be the case, but I just wanted to share with you the last update. And you can also see here the red and black, or red dotted line that kind of extends out from the power plant. I believe those are their transmission lines. So that delivers the hot water out to Keflavik and to other parts in the Reykjanes Peninsula. So there's the hazard map that came through. And I found this little article and thought this was kind of interesting, just as a little bit of a side note. And so apparently the town council in Grindavik met, and well, not in Grindavik, they met in Reykjavik, but they were looking at all the fractures and cracks in town, and there's at least an idea out there that they might leave some of them as is and then make some sort of memorial, a monument out of them, maybe make it some sort of a tourist attraction. The idea being that, hey, let's fix the ones that really need to be fixed, the ones that are in the critical infrastructure area that, along major road arteries. But if we've got a crack running through some area that, like a tertiary road or in a neighborhood or a place that maybe isn't as high of importance, let's just leave them for now. And I think that's a good idea until we see how things play out. Whether they want to make it a historical or tourist attraction, I won't comment on that, but I would agree that let's just, let's fix the things that need to be fixed to keep the critical infrastructure and the roads operational, but let's not fix anything that's not necessary, at least right now, and let's just wait and see how this plays out kind of moving long term. So anyway, that's the update for today. Let's go right to the questions that folks had, and I've got maybe 10 or so of these here. So let's start with this question from Ken. Does a hotspot volcano tend to produce a different type of magma? And he lists different types of magmas or lavas here: basaltic, andesitic, rhyolitic. This just goes with how much silica it is. Basaltic magmas, that's what we expect here in Iceland. It will be runny, high temperature, typically non-explosive, versus at the other end of the spectrum, a rhyolitic eruption is going to produce much more, has going to have a lot more silica. It's going to trap gases, and it's going to therefore be much more explosive typically. So does a hotspot volcano tend to produce a different type of magma than a divergent zone or even a subduction zone? Probably a good, fairly simple way to think about this, and this might be, you know, not completely accurate and telling a tiny white lie, but it's a good way to think about it. All magmas fundamentally start out as basaltic. And so, depending on what they're rising through or what happens to them, they can evolve into other magma types, or if they can get to the surface quickly, then they'll generally stay basaltic magmas. So, for example, divergent zones in where the plates are spreading apart, like we see in the ocean, those produce dominantly, like in the Iceland's a good case study in this. It's like 96% whatever basaltic eruptions. If you look at other parts of the mid-Atlantic ridge, it produces, I think, almost exclusively basaltic eruptions. Hotspots, hotspots are a little, well, hotspots in the ocean are much the same. Hotspots come from a much deeper source, and so those deeper sources will produce basaltic magma. And if that basaltic magma is rising and it's running through the ocean crust is also made out of basalt. So if you have basaltic magma moving through basaltic crust, you get basaltic lava at the surface. And that's what we see in ocean basins. In the case of hotspots under continents, though, like Yellowstone, we have basaltic magma that's running into a very thick, maybe like 60-kilometer thick section of crust that is not basaltic in composition. It's mainly granitic, meaning it's high in silica. So the idea there is that basaltic magma works its way through all that continental crust under Yellowstone. It starts to melt some of that granitic material, incorporates more silica, and so the type of magma that it can produce once it gets closer to the surface is rhyolitic, and that's why it's much more explosive. That's why even though Hawaii and Yellowstone are fundamentally the same volcanic settings, they're both hotspots. One is much more explosive and dangerous, although it erupts on very long timescales, right? And then Hawaii at the other end of the spectrum, non-explosive eruptions, but erupts more frequently. Hopefully that kind of helps a little bit. Okay, that sets the stage for his question, I hope here. I know that Iceland lies over both a hotspot and a divergent zone since Eyjafjallajökull lies farther west. So this is the volcano that erupted in 2010. It's further to the east of where we're looking at now in Iceland, and it was the one that shut down air traffic in Europe for several weeks. It was explosive because it erupted underneath a glacier, and that was the main reason. Is it more representative of a hotspot volcano, or would it still be primarily a divergent zone? So this is where it gets interesting, and this is just based on what I've read in about Icelandic geology. There's some debate over whether the non-basaltic magmas that are generated in Iceland, mainly east of the Reykjanes Peninsula, where the big mountains and the big ice caps are, there's some debate over whether those other magma types are forming because there's a little bit of continental crust underneath Iceland and the hotspot's coming up and it's changing its chemistry, somewhat like Yellowstone. And there's another school of thought that argues that these magmas are coming up from the hotspot, but they're evolving by fractionation, crystal fractionation. If you don't know what that is, don't worry about it. But basically, is that magma sits there for a long period of time and cools. You can change the chemistry of the magma a little bit by cooling it off. Crystals of one mineral form. The rest of the melt is different now in terms of its chemistry. Anyway, I don't want to get in too big there, but too big of a discussion on that. But there is some debate there over exactly what's happening there beneath that central part of Iceland, at least with the literature that I've read. So I don't know if I answered your question directly, Ken. Hopefully I did. Hopefully I gave it at least some insights there. From Håkan Svensson, living on the Thornquist zone in Sweden. Question about the epicenter of earthquakes. The epicenter is marked with a dot. Okay, remember the epicenter is the location on the map. The actual location inside the earth is what we call the focus. Okay, but especially in the case of strong earthquakes, it can be a several mile long stretch of a fault that moves. That's true. So when especially a larger earthquake occurs, the area of rupture, the place where the rock broke, isn't necessarily a point. It can be along a longer section of fault. Okay, but I assume it is of interest, among other things, because I assume that the tension is reduced on the stretch of the fault that is moved, but can in return increase on the parts of the current fault that have not moved. Tension is reduced on the stretch of the fault that is moved. Oh, I see what he's saying. Yeah, so this is absolutely true that when you have an earthquake, rocks have broken somewhere along a fault, stress has been relieved or released, but you can also load other sections of that fault with increased stress and cause it to have an earthquake possibly sooner than it might. So it's this idea of stress triggering, or it can be on multiple faults. You might have one fault that loads stress onto another fault when it has a specific earthquake. Yeah, so that's totally been looked at. Of course, we haven't figured out like how it works, or if it's definitely not predictable in the way of forecasting eruption or earthquakes, but has totally been looked at. Okay, so I haven't got to his question yet. Can geologists make such maps, that is, with lines for the entire earthquake instead of points showing the epicenter? So if I'm reading you right there, the epicenter would be generated quickly by the computers that use the seismic data. So they know multiple seismometers detect the earthquake, and we can use that data to pinpoint the epicenter, not just in two-dimensional space on the map, but into the ground as well, so we know how deep that earthquake is. We can generate focal mechanism solutions, the beach balls that you guys all know and love, that tell us a little bit about what kind of stress produced the earthquake, whether it was stretching or pushing or shear stress. So it tells us a little bit about the orientation of the fault and the stress involved. And if the earthquake is big enough that it ruptures the surface, you can definitely make a surface rupture map that shows how much of the ground was displaced during the earthquake. I don't know, because I'm not a seismologist, if you can generate a subsurface rupture map from seismic data. I think they probably can, but I don't know exactly how or anything else about that. So hopefully I helped a little bit with that. From Horst in Germany, my question is simple. How can they measure the inflow of new magma into the dike? Yeah, so really good question. Because we've talked about this before, they know new magma's coming into the dike, and sometimes you see them give numbers like, oh, we've got 50 cubic meters per second of inflow into the system, and you're like, well, how do they know how much magma is actually coming into the shallow subsurface? So what I'm going to do to show you how we figure this out, it's an estimate based on numbers, but it's a pretty simple calculation. So we need to first start with the area. So let's say we have an uplifted area that's, I don't know, 50 square kilometers, okay? So the first thing we're going to do is we're going to turn that, and there's nothing more exciting than watching someone do math. So I'm going to do math with you, and you're going to be entertained and educated. So hang on tight here, team. So 50 square kilometers, if we want to turn that into square meters, then we would need to times it by 1,000 twice. So 50 times 1,000, and then another 1,000. So let's add some commas in there. So 50 square kilometers is the same as 50 million square meters. Okay, so there's our area of uplift. Like a piston, we've uplifted some large area of the Earth's surface. Okay. The other thing we need to know is the uplift. And let's say the uplift is kind of like what they've been seeing around this area in Iceland. Let's say it's 10 millimeters per day. 10 millimeters per day is 1 centimeter per day. And that is also equal to, if we turn all the meters, we need our units to be the same. You're remembering all this from school, right? All that math that you groaned and moaned through, it's all relevant now. Let's put this on a separate line. Okay, so hopefully you're with me here. So we've uplifted this much of an area with 10 millimeters per day. So we're going to pretend it's all a piston. Now in reality, it might be bowed up more in the middle, less uplift along the margins, more uplift in the center. But to keep this simple, let's just pretend a piston has pushed this section of the Earth's crust up at a rate of 10 millimeters per day. So to figure out the magma inflow, now we need to talk about volume. And volume is just like you buy your gas or milk by the liter, or in the States here we buy it by the gallon. It's a volume, right? So it's a container that has three dimensions to it. It's depth, its width, and its length, or whatever, or height. So we know we need to get this to we need 3 units. We need to get this to cubic meters. So we need 3 units of meters to make this work. So what we're going to do here is we're going to take that area, so 50 million square meters. Are you staying with me? Stay awake. This is important. And then we're going to times that by our rate of uplift. Some of the engineers they've already moved along because they've got this figured out. So if we times those two together, the rate of uplift times the area, if I did my math right, if I didn't, I'll hear from like all sorts of people that I didn't. We get 500,000 cubic meters per day. That's how much magma is moving into this area every day. A lot of times that's a nice number, and maybe that's handy enough for you. But a lot of times when we talk about rates of movement, especially things that are moving kind of quickly, whether it's a river or stream, or magma moving through the subsurface, a lot of times we use seconds instead of days. So I looked this up. I didn't know this off the top of my head. There are 86,400 seconds in 1 day. So if we take that 500,000 cubic meters per day and divide it by 86,000, last thing here, if you're ready to move on to something else, then this is the last little equation I'm doing with you. It's important to keep your units. This is something I preach to my students. So cubic meters, we'll just do it this way. I know the units are there. So we just need to divide it by the total number of seconds in a day. And that gives us, if I did my math right, about 5.8 cubic meters of magma moving through the earth towards the surface per second. Cubic meters per second, sorry. Hard to type and talk at the same time. So there you go. Hopefully that makes sense. So that's how we measure or estimate. Measure is probably the wrong word to use. We're not measuring it. We don't have a device that measures how much magma is moving into the system. It's just an estimate. So Horst, I hope that was helpful to you. Maybe that was just fun for you and I, and maybe a couple engineers or math people out there. The rest of you groaned and moaned through it, I bet. Okay, let's go to another one. Let's move this one down to the next page. From Georg in Germany. Many times you're talking about pyroclastic flows. What I know is they're from explosive volcanoes full of ash and debris and very hot gases. Very true. Good job. Here's my question. If the composition is mostly hot gas, why are they running downhill? Shouldn't they go up like other gas and ash plumes during volcanic eruptions? Thanks for your work. Best regards from cold Germany. All right, so we're going to talk about pyroclastic flows to warm up this good gentleman in Germany. So I did actually get something prepared for this one. So he's basically asking, why do pyroclastic flows follow the topography for the most part and stay on the ground rather than go up? They do have gas, but most of them, most pyroclastic flows are made out of dense material, hot rock and ash. And even though ash seems light, it's actually only carried upward by the gases and the buoyancy. So here's a cross section of a pyroclastic flow moving from left to right, and you can see the bottom has all these dense particles. There's sort of a turbulent circulation of gas and material, lighter material, that's on top here. But it's still, the whole point is, sometimes pyroclastic flows are also called, and you can look this up and Google it, it'll show up, PDCs, pyroclastic density currents. That's actually the more fancy scientific terms. I use pyroclastic flow because a lot of people have heard of it. But if we're writing a professional paper, we would use pyroclastic density current to describe this type of feature. And also I pulled up a video to show one of these. So here's one from Mount Merapi in Indonesia, just so you can see how these things behave as they move along the ground. You can see a big boulder rolling down there. but these hug the ground. There's still a billowing tail behind it where it's kind of rising. And this, even though this just looks like dust and debris, this thing would be, possibly over 1,000 degrees Celsius. This thing would be hot. If you saw this at night, it would likely be incandescent. So there you are looking at the tail where it is a little bit more less dense and it is rising a little bit, but it's the leading edge of that that really moves quickly and is so destructive. And this thing's probably moving, oh, I only know it in miles per hour, so you'll have to convert. They can move up to like over 100 miles an hour, whatever that is in kilometers per hour. I guess it'd be 160 kilometers per hour, so very rapid. Yeah, and they almost develop a little cushion. They almost have a low frictional surface as they glide. Looking at the physics of this stuff's pretty fascinating. So there you go. Hopefully that helps a little bit. So it's not mostly a gas. It's mostly dense rock and other volcanic material. From Susan Weimer. Okay, question. Are the new sinkholes in Grindavik due to the magma moving away from that area or another reason? Well, we don't think it moved away, right? So that magma moved from the area around the Blue Lagoon, and then on November 10th, it started to inject magma and form the dike, or I guess we call it, I'm calling it the magma intrusion, that was more or less kind of here. So that magma did not leave this area. It stayed there, and it's cooling and crystallizing as we speak. Maybe it's kind of mush at this point. It's definitely not eruptible magma at this point, based on all the indicators we have there. And so the sinkholes probably formed from the ground being pushed apart, and that's actually what caused some of the collapse there. So how will this affect people's return to their community? We don't know. If the sinkholes were, if the damage had been done and that's all we're going to see, then it would be pretty easy to go in there. They can fill in those sinkholes. They can put grout into them and fill material. They can repair the infrastructure, and they could be back up and running as a community probably by the spring. The big question, of course, is like, well, is there going to be more? Could there be another phase of activity similar to this? What about the lava? Is that going to come out onto the ground? Lots of other considerations there. From Pedro B. Quick question. I think you mentioned sticky magma and runny magma, silica content, etc. What's the reason that Iceland/Hawaii mantle rock is runny, yet the Stromboli, Etna, and Indonesian volcanoes have much more exploding sticky magmas? Is it due to the nature of the magma generation mechanism? Absolutely, and this kind of ties into the first question I addressed. So the type of magma that you get is largely determined by the tectonic or volcanic setting. So if you've got a divergent plate boundary like Iceland, that's also a hotspot, you should expect mainly basaltic magmas. If you've got a subduction zone like they have in Italy and in Indonesia, you're going to have much more explosive, or what he's calling sticky magmas. And that's partially due to in those locations, one plate's diving beneath another. It drags water that's trapped in the rock on the ocean floor down with it. That water then is, it reacts with the asthenosphere, a layer deep within the earth, and partially melts it. And that magma then comes up into usually continental crust or maybe evolved ocean crust, and usually it erupts. Well, it can erupt a lot of things. At subduction zones, you can run the gamut from basaltic eruptions to rhyolitic eruptions, but a lot of times they're actually kind of in between those two, more andesitic type eruptions. So hopefully that was a good take on that question. Just, yeah, it has a lot to do with the magma generation mechanism, which is dictated largely by the plate tectonic setting. I think we got two more team. Claudia, first, very earthquakes in Iceland. I'm concerned that the plates may have stuck. Oh no, that is not that good for plates. They have to move and actually make some little earthquakes all around. What does this mean? We have a stuck plate, we have a plume, we have dikes and chambers filled up with magma. Does the magma stop the plate movement, or stop the plate movement the magma? Chaos, right, Claudia? Who knows what's going on? It's welcome to Earth science. So the plates don't get stuck. Plate motion, though, is not like a conveyor belt. So the plates in Iceland, although they're spreading, they're not moving at a steady rate year after year after year. They do, I guess, in a way, get stuck, if you want to say that, but there's times where there's no movement, excuse me, and then there's periods of accelerated movement. You have a large earthquake, and now, boom, the plates have just moved, you know, half a meter apart or something like that. And then you go through years, if not decades, of no movement, and then there's another big earthquake. So when we say the plates are moving, a couple centimeters per year, that's an average rate of motion. It's not how much it actually moves year after year after year. So there's a lot going on. Yeah, like I wouldn't say that the plate's stuck, but we have a plate boundary. We have a magma mantle plume, which is mainly over further to the east in where the ice caps are in Iceland. But there may be some tail to that mantle plume in that hotspot. But we think that a lot of the volcanic activity in the Reykjanes Peninsula is driven by the plate boundary itself. And then she kind of gets to a question that has plagued geologists for a long time, and at least as far as I know, and I don't have my pulse closely on these things exactly, but maybe this isn't what she's asking, but she's asking about the magma versus the plate motion, and it's really a tectonic activity versus volcanic activity. Which one is the driver? Does the tectonic activity control the volcanic activity, or is it the other way around? And it really has become a chicken and the egg problem. There are clearly places where one seems to be the driver and the controlling factor. Other places where it's a little bit more murky. I'd say that this part of Iceland, the plate movement is the main factor, because we know that the hotspot, the main body of the hotspot, is further to the east. And so I'd say that the plate boundary and the movement on the plate boundary is the one calling the shots. It's controlling the action for the most part by relieving. It's generating the magma by relieving pressure on the underlying asthenosphere. So, okay, last question here from this person. One thing keeps bugging me. There's a lot of rumbling going on further east near Krishuvik, and this is supposed to be Klevervatn. Could it be that there needs to be a magma channel to the right added to your drawing? Today, there was even a lot of activity at Hengil. I'll show you where that is in a second. That's east of Reykjavik. The complete picture that's drawn before my mind's eye is that the tectonic movement drew Reykjanes northwest, and cracks formed in the ground that now get filled with magma roughly perpendicular to that movement. The quake started around Grindavik and spread to the northeast as if that were the line along which the ground tore open at some depth. Again, I studied some physics, no geology, so I declare geological cluelessness. Yes, there we go. I declare the same thing. To happily Dunning-Kruger on further, I'll say that this crack must be at some 5 kilometers depth, for even the quakes at Hengil are roughly at this depth. Okay, so a lot to unpack there. But what this person's getting at in general is that here's our earthquake activity, but they're noting that, hey, you've got clusters of earthquake activity over here, and we know that the last 3 times there was volcanic eruptions on this peninsula, it occurred on multiple volcanic systems. So while this is our primary focus, I don't think anyone's ready to say that 100% with 100% confidence this is the only place where we're going to expect volcanic activity. These other systems haven't done anything. We've had 3 eruptions in this area over the last 3 years, and they have not triggered or so somehow, based on the last 3 historic eruptions, it would appear as though these volcanic systems are at least connected at depth somehow. And that's where we just don't understand the plumbing system, right? We don't know the pipes and the tubes and the interconnections between these systems, what the triggers are. That's all a bunch of just unknowns right now. But that's what this viewer is asking about, is like, hey, maybe there's something here. And then he mentioned Hengil. So here's the capital, Reykjavik. Here's the ring road, Highway 1. And here's Hveragerði, the little town over here. And this is a very intense geothermal area. But you can see these earthquakes that have happened over the last day in this region near Hengil. This is the area he was talking about as well. So, I mean, I think the big question would be, is there connection between this earthquake cluster to this one to this one? I certainly don't know. I think, though, if you were to look at, I don't know this, but I would guess that if you were to look at a map like this from 5 years ago, before we had anything going on over here, there was maybe some earthquakes happening in some of these regions anyway, but I don't know. Remember, though, that this event over the last month here has changed the stress conditions throughout this entire region, and so I guess expecting the unexpected is probably the way to go, at least for now. So hopefully I answered your question. I'm not sure if I did, but that's, yeah. Could there be another magma channel to the right of my drawing? Yeah, it was a cartoon. It was just a diagram. I tried to keep it simple. I tried to stick with what was known. We know where we have the earthquakes. We know where the magma is, and we know where the magma went. And I didn't want to conjecture any beyond that for the most part. So hope this was helpful, friends. Thanks for joining me. I will provide, of course, other updates as needed, not necessarily daily, but just look for future videos coming out. I'm also repackaging some old Iceland videos I did out in the field there and pushing those out as well. So if you're interested in those are coming your way. Just wrapped up a bunch of trips, or a trip with a bunch of videos down in Southern California. So I'll be putting some of those together. I actually have like about 25 videos from here in the States that are needing to get launched. So I'll try to mix those in with the Iceland stuff and hopefully keep everyone happy, both the hardcore Iceland followers, the people who enjoy kind of what I've more classically done with videos. And I will get some sort of announcement out soon about a possible live stream on the 13th, which is a Wednesday. So I got to kind of look at my calendar and see what'll work. But hope you stay well. Hope everyone in Iceland stays well. Happy holidays to you. And enjoy your vacation time off if you get some. And if not, just enjoy the time you have. And we'll see you next time. Take care.